today in our next episode of the webinar series exploring nanomaterial synthesis using in situ microscopy. My name is Nienke Krantz and I'm an application specialist working from the European region. So as you might know from the title, this webinar focuses on the synthesis of nanomaterials, mostly focused on liquid cell microscopy. And this coincides with the launch of our new Triton AX system. What makes Triton AX so unique is its wide range in situ temperatures. It goes from all the way to -50 and really up to 300 degrees Celsius, which opens up some really exciting possibilities. Because now with all these temperature ranges, we can study materials that form in higher boiling point solvents, but also in the other extreme, or even study things freezing, lower doses, so many cool studies to be done. And now more about the series. We have a large variety and very experienced speakers in this series using in situ microscopy and liquid phase TEM for these type of studies for many years. So be sure to sign up for the other webinars as well. There's 2 more to come if I remember it correctly, so please sign up for those. A couple of housekeeping items before we introduce our speaker of today. Everyone is muted due to the audience size, so please enter any questions in the questions box in the GoToWebinar panel, and then I can help read these out to our speaker for you. And the Q&A session will be at the end of the webinar. We will have a survey pop up as well at the end, so we really appreciate if you could fill that in. It only takes about a minute. So those are the household items, and now I can actually introduce the speaker of today's webinar. We are absolutely honored to have Dr. Damien Alloyeau speak on the topic of exploring the nucleation, growth, and self-assembly of metal nanostructures with in situ microscopy. Damien is a CNRS Director of Research at the University of Paris Cité. And following his PhD thesis on the thermodynamic properties of magnetic nanoalloys performed at the French Aerospace Lab, ONERA, he was hired as a postdoctoral fellow by the Lawrence Berkeley National Laboratory to develop phase contrast imaging techniques at the National Center for Electron Microscopy. He joined the Materials and Quantum Phenomena Laboratory as a permanent CNRS researcher in 2010. And since then, he has worked on the fabrication and the atomic scale characterization of nanomaterials with the view to establish the links between their structure and their properties. Transmission electron microscopy, TEM, still serves as a cornerstone of this research, particularly in situ investigations in liquid and gas environments to understand the dynamics of nano objects in their formation and application media. So thank you so much for joining us, Damien. And I give the floor to you. The presentation is already up, and I'll mute my camera, mute myself and remove my camera so you can speak, but I'll be back at the end. Thank you. Good luck.
Okay, thank you very much, Nienke. Thank you for this very kind introduction. Good morning or good afternoon, everyone. It's a real pleasure to contribute to this webinar series. Thank you to Protochips for inviting me and giving me the opportunity to show you some of the work we do in Paris to explore the synthesis of nanomaterials with in situ microscopy. So as Nienke told you, my group is working on the fabrication of nanoalloys mostly, and at the same time we are running a national user facility for transmission electron microscopy, including state-of-the-art instrument. And with this dual role, we have the opportunity to exploit the multifunctionalities of transmission electron microscopy to establish the link between their structure and their properties. But we rapidly realize that if you want to fully understand the development cycle of nanomaterials, you need to establish the link between the structure and the properties is not enough. We clearly need to also establish the link between the fabrication and the structure at the end of the synthesis. And for that, you crucially need to understand the nucleation and growth mechanisms. And if you want to improve also the performance, you need to establish the link. You need to know if and how those wonderful structures that you have fabricated, if they transform when they are at works during their application media. And that's the reason why for 13 years now we have been working with the Protochip gas and liquid cell systems with the idea to study the dynamics of nanomaterials in their formation and application media. So a brief reminder of how those sample holder works, the Poseidon, Select, and atmosphere systems. The idea is to encapsulate the liquid and gaseous environment with those silicon nitride, those heat chips. So solid chips, they are a silicon wafer on which you have a window that is covered with a silicon nitride films that allows to seal the liquid or gaseous environment, and you can control the composition of the environment by injecting any type of liquid or gaseous of gas at the observation windows. And with this, you can observe the dynamics of nanomaterials in liquid media of controlled composition and also of controlled temperatures. So as I told you, we apply this technology to study the nanomaterial synthesis and also those transformation and degradation processes in their application media. But for the talk call today, I will only focus on the nucleation and growth mechanisms. So the take-home message of my presentation is the following. So size, shape, composition, and atomic structure of nanomaterials relies on the competition between kinetics and thermodynamic effects that can be tuned with rational synthesis strategies. And whether you are using physical methods or chemical methods to prepare your nanomaterials, what I want to show you is that you can use in-situ TEM as a guideline to rationalize your synthesis protocol and establish new strategies to control all the structural parameters of your nanoparticles. So what I mean by kinetic effect is usually the growth speeds, and what I mean by thermodynamic effect is the structural stability of your materials in its given environments. And I want to show you that you can really use in-situ TEM to better understand this competition between kinetics and thermodynamic effect. And actually, it's a very old idea in my groups, because I want to show you as an introduction a very old experiments that we did that I did during my PhD. So almost 20 years ago. The idea of my PhD at the beginning was to fabricate cobalt platinum nanoparticles in this chemically ordered structure, L10 structure that you see here, because those nanoparticles, they have a very interesting ferromagnetic magnetic properties that allows to have a permanent magnet even when they are very small. So the idea was to fabricate small, below 3 nanometer nanoparticles with this specific structure. And we used pulsed laser deposition technique, which is a vapor phase deposition technique, to obtain those nanoparticles. And so we deposit, we use a laser to fabricate, to interact with pure metallic target, and we do an alternative deposition of those metals on a substrate to fabricate those nanoparticles. And we were very surprised at the beginning of my PhD to obtain nanoparticles. We were fabricating those nanoparticles between 300 and 500 degree temperature. And we were very surprised because if you look at the bulk phase diagram of the cobalt platinum system, you see that at this temperature, the thermodynamic equilibrium of the system is this chemically ordered structure. But when you obtain the Asgrown nanoparticles in this temperature range, they were always chemically disordered, so the high temperature phase, FCC. So we wanted to better understand why we had this out of equilibrium structure. We decided to do an in-situ heating experiment to directly observe the morphological and structural evolution of the nanoparticles as a function of the temperature. And this experiment is shown here. When you increase the temperature, you see that at 600 degrees, it takes about 10 minutes to see the apparition of the chemical order. At 700 degrees, you see that you have a lot of growth mechanism and a drastic size increase of the nanoparticles. Your particles are well ordered. You see the superstructure reflections. And then at 750 degrees, you see the phase transition that is seen here on the bulk phase diagram. It's purely thermodynamics here. So from this experiment, we can understand what I mean by kinetics versus thermodynamic competitions. You have this out of equilibrium structure because by PLD, it takes about 10 minutes to fabricate those particles. But if you work at between 300 and 500 degrees to synthesize your particles, it takes more time to obtain the chemical order than to fabricate your nanoparticles. And that's where you are dominated by kinetics. So from this experiment, we see that if you want to have small nanoparticles, you should work below 700 degrees, but you should work above 600 degrees to have the chemical order in a reduced time, less than 10 minutes. And from this experiment, we could say, okay, if you want to obtain small cobalt platinum nanoparticles that are chemically ordered, you need to work at 600 degrees. And that's what I mean by, if you want to use TEM to improve the synthesis, you need to use it as a guideline. and to better understand this competition between kinetic effect and thermodynamic effects. So nowadays, more recently, we have been working on more complex nanoalloys. We work on high-entropy nanoalloys. So those nanoparticles, they consist in a mix of up to 5 metals that crystallize in a solid solution if they are, if in your nanoparticles, you are near the equiatomic compositions. And they can end up in the FCC, BCC, or hexagonal structure. And those nanoparticles, they are expected to have very potential application for high temperature, at high temperature, so anti-corrosion, mechanical properties, and especially high temperature catalysis, because they are expected to be extremely stable. And the reason for that, there are a lot of speculation about the properties of those particles. They are expected to be stabilized by the entropy, and by the fact that because of the lot of lattice distortion and the different size of atoms that you have in this nanostructure, they expect to have a lot of sluggish diffusion. So the first question we ask working on those systems, are they really stable? Is the stability of high entropy nanoparticles true? So we designed an experiment using now the very highly stable gas cell system from Protochip, an in-situ TM experiment to verify these hypotheses. Are they really thermally stable? So we fabricate those nanoparticles using PLDs, the same synthesis method that to obtain the cobalt platinum nanoparticles. So you are using a laser to irradiate metallic target, you create a plasma, and you condense this plasma on the surface. So we had the nanoparticles, and we use the Protochip gas cell system under vacuum to observe the thermal behavior of those nanoparticles between 500 and 700 degrees, and using high resolution and EDX analysis in STEM mode. Here is the starting points of this experiment. So the as-grown nanoparticles, you see you have particles of roughly 5 nanometer. You are close to the equiatomic compositions. Small nanoparticles are mostly monocrystalline, but the larger nanoparticles are usually polycrystalline. So that's the starting points. And then you start eating those nanoparticles, and you realize that in fact they have a very classical thermal behavior, exactly as the bimetallic systems. You increase the temperature starting from 400 degrees, you see a decrease in the density of the nanoparticles, and you also observe a 3D growth. So your size increase, a decrease in the density, and you also see that the aspect ratio of the nanoparticles goes to close to 1, meaning that you have a 3D growth of the nanoparticles. They become small sphere, in fact. And this starts from 400 degrees. So you see that it's even way below the temperature where you see these coarsenings in the bimetallic system. I've shown you the cobalt platinum nanoparticle, but it's also true for other systems. So in fact, first conclusion, there is no sluggish diffusion in these finite size high entropy nanoalloys. So the main mechanisms driving the size increase of the particles is coalescence. And here I show you that at 500 or 600 degrees, it takes a few minutes to obtain the coalescence. At 700 degrees, it takes a few seconds. Very logic, because it's a thermally activated mechanisms. What I want you to see here is that each time we have a coalescence event, we observe a strong contrast area in the nanoparticles that indicates segregation of the metals within the nanoparticles. Keep that in mind for the next slides. Of course, if you want to know more, you need to work at higher resolutions. So we obtained, or we also studied these nanoparticles during this experiment at high temperature with high resolution. The images are fantastic. It shows the stability of the sample holder, but at the end, no much change regarding the structure. From 25 to 700 degrees, particles remain in their FCC structures, monocrystalline or polycrystalline. It's more interesting to study the spatial distribution of elements. We realize that in the nanoparticles that did not coalesce, you have an homogeneous distribution of all the elements in the nanoparticles. But in the particles that have coalesced, the big particles that you see here, where we saw this different contrast area within the nanoparticles, with EDX, we prove that in fact we have a segregation of gold and copper at the surface of the nanoparticles. So gold and copper wants to go at the surface, and it's accelerated by coalescence. Now, the most striking result of this experiment happened at 700 degrees. 700 degrees, you see, we observe just after reaching this temperature step, we observe a size decrease of the nanoparticles, 25% reduction of the nanoparticle size. Here you see this on those images, and here on this diagram, you see that we completely lose the gold and the copper from the nanoparticles. So those two metals leave the nanoparticles and evaporate in the microscopes. And when you do the chemical mappings in the nanoparticles, you only have cobalt, nickel, platinum left in the nanostructures. So it means that we have a segregation of cobalt, of gold and copper, and those two metals evaporates. And when you look at the numbers now, if you want to understand what's going on, the first thing you look at in the system is the surface energy. And it turns out that gold and copper have the lowest surface energy. So it makes sense. Okay, if you want to minimize the energy of the systems, those two metals have to go at the surface. If you look at now the melting temperature, gold and copper have the lowest melting temperature. And we know from other experiments that gold, copper nanoparticles, if they are small, they evaporate at 700 degrees under the vacuum of the microscope. So this experiment makes sense. But if you want to better understand the full structural purposes of those nanoparticles, taking into account the energy, the surface energy is not enough. You have also to take into account the alloying effect, the ability of all those metals to create links with each other. And to do that, you need to go through atomistic simulation. So we collaborate with Hakim Amara and Anissa Ashesh from the LPTEM at Zionera, who have been able to calculate using a published potential of the same nanoalloys, of the same alloy, to calculate the equilibrium structure starting from icosahedral nanostructures, the tendency of segregation at different temperature. And this confirms that the structural properties of those particles, the thermodynamic equilibrium of those nanostructures, is dominated by surface effects. It's dominated by the, we clearly observe when you increase the temperature, you have a segregation of gold and copper that you observe here, while the other metal goes below the surface. So the temperature increase the segregation effect, and it means that the structural purposes is dominated by the surface energy of each individual metals. Now, my colleague have been also able to demonstrate that by running simulation on two very close high entropy nanoalloys, they have been able to simulate the coalescence of two clusters, and they realized that there is a much higher segregation effect of gold when those in the coalesced nanoparticles with respect to the single nanoparticles. And this effect is due to exactly the result that we also observed experimentally. And they have been able to prove that this effect is due to the fact that when the particles coalesce, you have because of the restructuration of the nanostructure during coalescence, you have a much higher diffusivity of the gold inside the nanostructure. And as the gold, as the diffusion of gold goes faster, you reach faster the thermodynamic equilibriums where gold atoms wants to be at the surface. So take home message from this experiment: there is no sluggish diffusion in these high entropy nanoalloy systems. The structural purposes are not dominated by the entropy, they are dominated by the surface effect. And as the thermodynamic equilibrium of those nanostructures is the phase separation of gold and copper under vacuum, it means that if you want to fabricate those high entropy nanoalloys with an FCC structure, you need to go fast during the synthesis because they are still stabilized by kinetic effect. And that tells you that you should not believe everything that you can read in the literature about those systems. You have to study it, study the structural purposes. But pay attention, take home message also, very important message, the environment is also extremely important. So if you work in a synthesis condition that is oxidizing, you should follow this recent publication that we did, exactly the same in-situ heating experiment, but this time under 1 atmosphere of oxygen using the gas cell system from Protochip. And this time when you work in an oxidizing environment, it's not the gold and the copper that goes at the surface. You have a segregation of nickel and copper, that are the two metals that have a lot of a strong oxidizing behavior. And this time you have the formation of these nickel cobalt oxide platelets in between the nanoparticles, or at the surfaces of the nanoparticles. And due to Kirkendall effect, the remaining platinum, gold, and copper nanoparticles present some voids due to the Kirkendall effect, the fact that the diffusion of the nickel and the cobalt toward the surface is faster than the insertion of oxygen within the structure. So let's leave a void inside the nanostructure. So keep in mind, of course, the structural transformation of your materials during the synthesis are affected by the environment. So in the second part of this talk, I'd like to show you that my take-home message also apply for wet chemical synthesis. And of course, in that case, you will be using liquid phase TEM. So usually one of the main advantage when you want to study the synthesis of materials with liquid phase TEM is that we can use the radiolysis of the solvent as a driving force. So radiolysis, when your electron beam interact with a liquid sample, the radiolysis the electron beam can radiolyze your solvent. And in the case of water that I show here, you create a lot of radicals and molecular spaces, and some of them, such as these aqueous electrons or the hydrogen radicals, can reduce the metallic precursor that you have in the solution to the metallic state to induce the nucleation and the growth. But what is very interesting is that the electron dose rate allows controlling the concentration of reducing agent. So now we have a way to control the kinetics of the reactions and the thermodynamics of the environment by controlling its composition. So we have a great tools to distinguish between thermodynamic and kinetic effects. So first experiment that we did when we had this sample holder 10 years ago now, we did this experiment with a gold chloride solution, 1 millimolar in very low dose rate condition. And here you observe the growth of well-faceted nanoparticles. And what is interesting is I show you here what's going on when you the size, the evolution of the size of the nanoparticles as a function of time for 3 different magnification. And when you work in STEM mode, when you increase the magnification, you put the same beam energy over on a smaller area, so you increase the dose rate. And you see that when you increase the dose rate, we increase the growth speed of the nanoparticles. So now we have a way to see the effect of the growth speed on the shape of the nanostructures. And here is the result. When you are at low dose rate, so low growth speed, you observe these well-faceted nanoparticles. Have you seen the growth mechanisms in the previous slides? And here you have those well-faceted nanoparticles because you are governed by thermodynamics, meaning that the deposition rate is much lower than the surface diffusion rate. So you are dominated by surface diffusion, and you give enough time to the system to reconstruct those well-faceted nanoparticles. Now, when you increase the growth speed, you start having those branched morphology and even those dendritic morphology, because now you are governed by kinetics, and your deposition rate is much higher than the surface diffusion rate. And from this experiment, almost 10 years ago, we have been able to see that the formation of faceted nanostructure require reducing the reaction rates below 3 atomic layers per second. Now, more recently, we studied exactly the same type of experiment, but taking into account the temperature. And to do that, we used the sample holder, the liquid cell developed by Protochips, where you have a resistance that is embedded inside the silicon wafer that allows you to control the temperature of the whole liquid cell from 25 to 100 degrees. So we don't have the Triton, sample holder that allows you to go to higher temperatures. So this experiment from 25 to 100 degrees. And actually, temperature is an extremely just as when you work with vapor phase deposition, temperature is a very, very important parameter during the synthesis, because any atomic scale mechanisms is temperature dependent. In the solution, the reaction, the solubility, and the diffusion of metal precursors depends on temperature. At the surface of the nanoparticles, the nucleation, the absorption, desorption, diffusion of metal atoms depends on the temperature. And even when you work on more complex systems than gold, I've shown you that for the cobalt platinum system, for example, the thermodynamic equilibrium towards your system wants to go also depends on temperature. So if you want to understand anything about temperature effect, you need to see, to visualize what's going on. And I show you only one part of the result, just about the shape, what's going on when you play with the temperature. What is interesting with this experiment is that the deposition speed increase with both the dose rate and the temperature, but the diffusion of metal atoms at the surface only increase with temperature. So now, by playing with both dose rate and temperature, we have a way to visualize the effect of this competition between deposition rate and diffusion rate. And the result is shown here. You at low dose rate, so low growth speed, so you give a lot of time to the system to reconstruct. In both cases, low temperature and high temperature, you are dominated by surface diffusion, and you reconstruct nanoparticles that are mostly made of 111 surfaces, which are the most stable surfaces in gold, in FCC systems, most generally. And when you work at high dose, I've already shown you that at 25 degrees, you grow nanoparticles that are dendritic with rough surfaces, with high index facets. So you reconstruct facets that are theoretically not stable because you are dominated by kinetics. But if you work at 85 degrees, you compensate this high deposition rate by increasing the temperature. You increase the diffusion rate, and you reach another type of shape of nanoparticles. You start growing nanocubes that are made with 111 weight, that exposed 100 surfaces. So this experiment show you that when we have no way to visualize what we call the nanophase diagram of nanomaterial synthesis, meaning what type of shape you can obtain while playing with kinetics and thermodynamic effects. And actually, this experiment perfectly illustrates the theory developed by Professor Xia at Georgia Tech University, where we have shown that starting from palladium cubic seeds, by playing with the diffusion and the absorption rate and the deposition rate in a beaker, when you want to play with the deposition rate, you play with the redox potential or concentration of your reducing agent. And diffusion is we play with temperature, and they have clearly demonstrated that you obtain branched morphology when you are dominated with by deposition rate, and they obtain nanoparticles with 111 facet when you are dominated by diffusion rate. But in the middle, you have an intermediate regime when your cubic seed keep growing as cubes and ends up with very nice 100 facets. So this experiment confirms existing strategies in nanochemistry. Now, another way, if you want to play with these, another way to play with this faceting mechanisms is obviously to play with the functionalization. And at that time, we wanted to answer the question: can we observe the effect of molecules on the growth process? So in this experiment, we started from the low dose rate experiment, where we grow well-faceted nanoparticles, and we have studied the shape distribution of those particles. And you see most of them are made with decahedral nanoplates, icosahedral nanoparticles. You have also some rods and some irregular shape, but most of the nanoparticles are decahedral and icosahedral nanoparticles. You see here the tomography experiment on the high resolution image of those icosahedral nanoparticles. And so we grow those seeds, and we use those seeds to observe the effect of the dimethylamine molecules. So during the growth, we stop the experiment, and we start injecting this dimethylamine, and we observe the effect of this molecule on the growth process. And when the molecules are in, the icosahedral nanoparticles, they stop growing as icosahedral, and you have a stellation process where you have arms that grow on the 20 facets of the icosahedral nanoparticles, leading to the formation of uniform nanostars. And I show this example because I want to show you that, in fact, this stellation process is, in fact, not in agreement with the common view of crystal growth. If you look into textbooks, you'll see that this sentence that says that the habit of a crystal, the shape of a crystal, is determined by the relative rates at which different crystal planes grow. And this sentence is well explained by this experiment, the growth of a platelets. Here you observe you have a triangular platelets that is terminated with 4-2 edges, and during the growth process you have a restructuration of the tip of the triangular nanorod, triangular nanoplates, and the atoms grow along the 4-2 directions. So another way to say this sentence is, if the atom depositing on a given facet, here's the 4-2 facets, this facet will grow out of existence. And you end up with this process. You see that you end up with a platelet that has 200 edges. So if you apply this common view of crystal growth to the experiment, the stellation process due to the dimethylamine molecules, what you expect to see is you have these icosahedral nanoparticles with 2111 facets, and you expect the dimethylamine to stabilize one given high index facet, HKL facets here, and the atoms will then deposit on the 111 facet, so the 111 facet will grow out of existence. So you expect to see at some point during the growth truncated arms, 111 truncated arms. And when now you observe the growth process on this video, you see that in fact we never see those truncated arms. The growth process goes like if you were pulling outwards on the arms, on the 20 arms of the nanostars. And this implies that the index of the nanostar facets continuously change during the formation of the nanostars. So you see this type of in situ experiments make us realize that we have to reconsider the effect of organic functionalization on the growth mechanisms. It does not stabilize a given facet. These alkylamine molecules modify the surface diffusion mechanisms. So in fact, the effect of functionalization, it's not a thermodynamic effect. It drastically changes the surface diffusion pathway of atoms to end up in another equilibrium structure. So the whole mechanism is different. So we should stop only look at the final result of a structure and think only with thermodynamic equilibrium. The whole mechanism is different. What I wanted to show you with this study was that liquid cell TEM can be used as a guideline to optimize the synthesis protocols, exactly as we did with the in-situ heating experiment on the nanoalloy systems. And we work on in collaboration with the Itodis laboratory in the chemistry department of the University Paris Cité. We worked on the biotemplated synthesis of gold nanoparticles on tobacco mosaic viruses. And what we wanted to have is to optimize the optical properties of those nanoparticles. We wanted to have a very large absorption bands, plasmonic absorption bands for those nanoparticles. And the key for this is to obtain a very high density of nanoparticles, of small nanoparticles at the surface of the TMV virus. So the only question we wanted here and to answer here is how to increase the density. So we designed this in situ experiment, and we see that we can follow the growth of nanoparticles at the surface of these TMV, of those viruses. We see that the density of nanoparticles is much higher at the surface of the viruses, which confirm that there is a strong interaction of the negatively charged chloruric acid with the positive charge of the virus capsid, which induce the nucleation of nanoparticles at the surface and their growth. And as the density is already very high, we also have a lot of coalescence. And that's what you want to avoid if you want to increase the density. So we did an experiment where by increasing the dose rate, we see that we increase the growth rate of nanoparticles at the surface of the virus. And we compare this result with a bench scale synthesis where we use NHBH4 to reduce the metallic precursors, and we do that through different reduction cycles. And we observe the result of the synthesis at each cycles. And you see when you increase the concentration of reducing agent, you increase the growth rate at the surface of the nanoparticles, at the surface of the virus. Now, what is more interesting to see is the effect of the dose rate on the nanoparticles density. And you see that when you have a very high dose rate for the first cycles, you have a strong nucleation burst. But then, if you want to avoid the decrease of the nanoparticle density, you have to have a growth of the nanoparticles, but it has to be extremely slow to avoid the coalescence. So from this in situ experiment, we have been able to see that if you want to improve the density of nanoparticles at the surface of the virus, if you want to increase the density of nanoparticles on the surface of the virus, you need to have a first cycle of reduction with a very high concentration of reducing agent, and then use additional reducing cycle with a very low concentration of reducing agent. And by applying this protocol on bench scale synthesis, my colleagues have been able to fabricate hybrid nanostructures with a density that is 10 times higher than if you are using reducing cycles with the same concentration of reducing agent. So that's what I mean by using in-situ TEM as a guideline. You can really improve your synthesis protocol just by observing it within the microscope. And here now we have this very interesting, very large absorption bands that is now applied, and those nanoparticles, those hybrid nanosystems, they are now used for cells detection, and they have very interesting performance for cells detections. Last example, I want to show you about the this competition between thermodynamics and kinetics. I want to show you that sometimes the size of your nanostructure can drastically affect their thermodynamic equilibrium. And in this experiment, we wanted to observe, to study a phase transition between amorphous structure and crystalline nanostructures that may occur in the very small size regime. So we designed an experiment using a graphene liquid cell. And here you observe the graphene liquid cell just after the first second of observation within the TEM. So we have again just the chloric acid solution within the liquid cells. And here you observe that just after a few seconds, the great majority of the molecules, the gold precursor, have been reduced, and you have this population of nanostructures. And when you do look at them at high resolutions, you realize that you have two populations. One is amorphous nanostructure in a size range from 0 to 2 nanometer, and you have crystalline nanoparticles in a size range from 1.8 up to 10 nanometer. You can clearly see that on this high resolution image here on the Fourier transform, where you see only the structure of the graphene, and the crystalline nanoparticles can be where you see the characteristic reflection of gold structures. Now, those nanoparticles, as I told you, most of the precursors have been reduced, so they are inside the nanostructures. So they grow, they keep growing, but now they grow as Ostwald-Ripning. And Ostwald-Ripning consists in the growth of the smallest nanoparticles at the expense of the big one. And that's what you see here. In fact, something that we have to realize, I come back, something that we have to realize when we talk about Ostwald-Ripning is the fact that nanostructure constantly exchange atoms with each other. You see here between those two nanostructures, you see that this one is increasing in size, this one is reducing, while this one is reducing. So you have an opposite, an anti-phase growth and etching mechanisms between those two nanostructures, because they are exchanging atoms. At some point, these small nanoparticles disappear because it's completely dissolved. So very interesting mechanisms to explain the size distribution of nanostructure, but here we used these change in size of nanoparticles, some grow, some are etched, to observe the effect of size on the structure of the nanoparticles. So that's the question we wanted to focus on. And what we see here you observe the full nucleation mechanism of a nanostructure. Occasionally you may have some nucleation mechanisms that occurs, and here you observe 4 little amorphous nanoparticles, nanoparticles. They are amorphous because they are below 1.7 nanometer, and when they reach a size range between 1.7 and 2 nanometer, you systematically have the crystallization. So this type of amorphous phase-mediated crystallization have been observed in many other systems, nickel, palladium, silver, and even in nanoalloys. And it's also well explained in the literature that it is one of the possible non-classical nucleation pathway that you can see in the formation of nanostructures. So this result is not very surprising, but the question you may ask is this amorphous phase due to kinetics, meaning that you grow the nanoparticles too fast, too fast, and you have an out of equilibrium amorphous phase? So to answer this question, is it due to thermodynamics or is it due to kinetics? We have the same, we wanted to know if we have the same phase transition during the etching. And that's what you see on this video. Here, you observe the isotropical etching of the gold nanoparticles in the liquid cell due to Oswald ripening. And here you observe, you see that when you have no ligand, this etching is isotropical. But here, at some point, when the particles goes below 2 nanometer, 2.3 nanometer, you'll see the loss. You see the crystal plane disappear, and then between 1.7 and 2 nanometer, it's actually switching very rapidly from the amorphous phase to the crystalline phase. And when it's below 1.7 nanometer, the nanoparticles are systematically amorphous. So the fact that you have this phase transition both ways during the growth or the etching of the nanostructure clearly indicate that this phase transition is governed by thermodynamics. It means that you have a thermodynamic equilibrium when the nanoparticles is below 1.7 nanometer. It's favorable to have this amorphous phase. And to confirm this result, we again collaborate with Hakim Amara, who has performed some Monte Carlo simulation in a tight binding framework. And Hakim has calculated the total energy of amorphous and crystalline nanostructure after relaxation for different size, of different number of atoms and different size of nanostructure. And you realize that the total energy difference between those two structures goes below kT, so you have a biphasic regime when the nanoparticles goes below 1.5 nanometer. So clearly these results indicate that there is a size-dependent amorphous crystalline phase transition in gold systems, and this result is due to the thermodynamic equilibrium of gold in this, it's a size effect on the structural properties of gold. To finish, before to conclude, I want to discuss a little bit the future challenge. What are the challenges in the field of liquid phase TEM? And I really like this graphic that you can find in the review, Nature review paper of Neil de Jong and co-workers, that shows the evolution of the resolution of liquid phase of microscopy as a function of the dose rate for a gold nanoparticles and a carbon nanoparticles. And you see, obviously, you reduce the dose rate, you reduce the resolutions. But this graphic also shows you all the beam-induced phenomena that can occur during your experiment. So if you work at high resolution, you have a very nice, very high dose rate, but above 10,000 electron per nanometer square, you start having hydrogen bubble formation, bubbles formation in water. You degrade proteins when you are above if you are not below the cryo-TEM of protein is usually done at 100 nanometer, 100 electron per nanometer square. The reduction of metal precursors goes way below, and if you see that if you want to avoid the damage of molecules, you need to go way. You need to reduce further the electron dose rate. So this is clearly the main challenge of liquid phase TEM. We need to further reduce the electron dose rate. And I'd like to show you two new tools that can be used to improve this trade-off. The first one is the use of electrostatic dose modulation. Here I'll show you a study where we work on the stabilization, the structural purposes of supercrystals. And the problem that we had is well exemplified in this video. When you increase the magnification, you increase the dose rate in STEM mode, and you destroy your nanocrystals. And we had a lot of trouble being able to study the structure of those supercrystals, because we needed a high enough magnification to observe the structure, but when you increase the magnification, you increase the dose rate and you degrade the nanostructures. So what we did, we use an electrostatic dose modulator, the IDES system, from that you can have on GL microscope. And the idea of this electrostatic dose modulation is to block. So it's an electrostatic shutter that works with a frequency up to 50 nanoseconds, and that allows you to block the beam at each pixel a given amount of time. So by reducing the dwell time at each pixel to compensate the increase in dose rate due to magnification, we are now able to observe those supercrystals without destroying them. We are able to reach a magnification that are high enough to observe their structure. And the most interesting result is that we have a way to study the structure of those supercrystals and obtaining the same type of structure, and more importantly, a tunable and controlled lattice distance, both that are in agreement from Sachs experiment and liquid cell TEM experiment. So really, these type of tools are extremely important to make experiment possible and much more easy to run. So that's really a great improvement for in-situ TEM experiment. And last thing I want to show you is sometime you need to drastically reduce the electron dose rate. Okay, it's necessary for your experiment, and then you will not see anything anymore. So in that case, what we have developed is a deep learning assisting denoising of liquid STEM images. So we used a deep learning approach to improve the signal to noise ratio of liquid cell STEM images. So here I show you an example where you have gold nanoparticles that are in the liquid cell, and the main problem of this image is that our eyes actually are actually fantastic detectors. If you ask a kid to draw around those nanoparticles, he'll be able to do it because you can see it. But if you ask a computer to binarize this image, actually it's a nightmare because the noise is actually very high. Here the signal to noise ratio of those particles is between 1 and 2. And you also have a very inhomogeneous background because you have a lot of particles that grow on the outer membrane, so they are highly out of focus, so they contribute to this inhomogeneous noise. So if you want to improve the signal to noise ratio and be able to treat automatically this type of image, you need to work on deep learning approach, and that's what we did. We use but to train our UNet networks, we use kinematic STEM HADF simulations. that allows us to take into account the variety. The key is to take into account the variety of size, shape, and orientation of your nanostructure within the liquid cell. So that's what we did. We put a lot of different type of shape and size of nanoparticles. And then you calculate the noise-free image that consists only in the thickness of the nanoparticles at a given point, multiplied by the Z atomic number. So it's very simple atomistic very simple kinematic simulation. Then you have to take into account the noise of your image. And to do that, you take into account, you had the out of focus nanoparticles, and you take into account the liquid broadening by changing the convolution of your probe, and you add a Poisson noise. And you end up with those noisy images that are very similar to your experimental image. And when you have a unit network, you give him the noisy image and the noise-free image. You train it to optimize the noisy image, and now he's able to give you these liquid cell TEM experiment with a very much better signal-to-noise ratio. So just to show you how efficient is it, I show you here the segmentation of those raw data. So you do the manual measurement of the size distribution of those particles. You have a bimodal distribution. When you treat those data with conventional treatment, using a bandpass filter, for example, or if you use other type of AI approach to denoise those images, you end up with size distributions that does not look like the one that you do obtain manually. But with the aqua denoising software that we have developed, you are able to obtain this automatic segmentation that is very close to the very similar to the manual segmentation, and you can do that automatically. So what are the main advantage of these new methods? We will be able to perform in situ STEM experiment at much lower dose rate and recover the loss of signal-to-noise ratio with the AI approach. You can, most importantly, this approach can be easily adaptable to other materials and beam-sensitive materials. It takes only a few hours to train the networks. Again, what you have to take into account is the composition and the variety of size and shape that you have in your liquid cell. And those treatments, they are extremely fast. So on-the-fly denoising, meaning can be considered. That's what we are working on now. The idea to obtain image on the microscope that will have this quality. And the take-home message is also this approach. It's published in this paper, but the code are in open access. So if you want to improve and adapt this method to your own materials, please go see these articles. So as a conclusion, I hope I convince you that in-situ TEM is a great tool to rationalize the nanoworlds and stop guessing about the formation or transformation of nanostructures in their formation or application media. And of course, I want to thank my co-workers at the MPQ Labs, in other laboratories, the funding agency, and I thank you for your kind attention. And I will answer any question you may ask. Thank you.
Thank you so much, Damien. That was an awesome presentation. Really great combination work between gas cell, liquid cell, all the nanomaterial synthesis. Really cool to see. We already have a bunch of questions, so I'm just going to go through them one by one and see what we can do in the time. But the first question is, and if there's any questions left over that we cannot answer, I can email them to you, and you can discuss with the people personally.
Of course.
Yeah, so the first question is, as coalescence is an exergonic process, there can exist a transient disordered state. In that case, how can atomic positions be determined, as the imaging would be limited to the projection and dechanneling effects?
I'm not sure if it's. I think it's related to the.
It's the beginning.
The beginning or the
I think it's beginning
the
to the gas
okay,
cell.
okay,
Yeah, to the gas cell start. Yeah.
Can you repeat the question so I can understand
Yeah.
it?
So as the coalescence is an exergonic process, there can exist.
Hexagonic.
Yeah, I think it's. I think he means maybe exothermic. I think.
Okay,
But I'm not sure. In that case, how can atomic positions be determined? As the imaging would be limited by projection and dechanneling effects.
Okay, so first of all, I think where we see the during the coalescence, I think he talked about this image. We are most. Of course, there will be the channeling, but we look at those images at low resolution. So I mean, there is no doubt that there is a segregation of metals, of the different metals within the nanoparticles on those images here. I'm not sure if I understand what he means by it's exothermic. To me, it's thermoactivated. It was extremely difficult we tried to observe this process at high resolution, but it was quite challenging on this system. I'm not sure. I wonder if if the question could be related to the fact that we use kinematic simulations in the aquadenoising methods. Okay, can the person precise the question if what he's talking about?
Yeah, he elaborates that exergonic, it adds energy to the system.
Okay. I don't see the link with the channeling effect. I'm sorry, but yes, of course, coalescence is a way for the system to reduce the surface energy. To me, the question is not very clear. I'm sorry. Maybe the person can contact me by email. We can discuss further about this.
Exactly. We can always put you in contact, and that might be helpful to discuss it further.
Yes.
So another question is on the liquid cell part about the star nanostructures, and then about the morphology plane of 4 to 1. Can that increase diffusion? Comparing this to other structures. So does the diffusion depend on the nanostructure morphology? Basically, the diffusion of the
So we as we see on this video, the growth is very continuous on it does not slow down over time. So the diffusion mechanism seems to be actually the diffusion mechanism and the growth of those nanoparticles from the kinetic point of view, it's affected by the concentration of dimethylamine. I did not show this result, but when you increase the concentration of dimethylamine, as I say, you change the diffusion mechanisms at the surface of the nanoparticles, but you on average, increasing the dimethylamine concentration reduce the growth speed, first of all. And then when you increase the concentration, you favor the formation of the arms, because in fact the diffusion mechanisms you obtain nanostar with sharper arms when you increase the concentration of dimethylamine, because the sharpness of your arm is a competition between the length of the arm and the size of the core. And by increasing the concentration of dimethylamines, you increase the growth of the arms, and you reduce the growth of the core. So you obtain sharper arms.
Yeah, awesome. Then another question is for the high entropy alloy work. Did you perform or is 3D EDS tomography, or did you perform 3D EDS tomography to show the distribution of gold in the high entropy alloys? And then she has a second question on the, but let's first do the first one because otherwise it's too much. So did you perform 3D tomography basically?
It was not possible to do tomography during the in-situ experiment because the protochip holder has a very limited tilting range. So no, we did not do that. If you want to run tomography, you have to do it ex situ after the experiment. So you unseal your gas cell. You can take the small or the larger chip, and yes, in that case, you can run tomography. No, we did not do that for this experiment. And yeah, I know it's possible to do a three-dimensional chemical mapping with this technique, but it's a lot of work. So no, we did not. It would have been very interesting, but no, we did not do it.
Yeah, no, clear. And she has a second question. I'll do this question, then one more short question, and then we'll wrap up. A second question is, and I'm assuming this is about the graphene liquid cell work. I'm not 100% sure, but she's saying an amorphous looking FFT does not necessarily mean the particle is amorphous. It could also mean that the crystal is just not oriented close to its own axis, or that the particle is too small or too defective for clear spots to appear.
Very interesting question. Very interesting question. Thank you for asking that. Yes, that's something we took into account, and what we did to prove these points, we have a very good resolution on those images. About you see here about one angstrom resolution here on those images, and what we did with this type of resolution, we simulate the structure of crystalline nanoparticles, 1,000 image with various orientation. And it turns out that only 4% of the images show a crystalline nanoparticles that would look amorphous, meaning that the angular range along which crystalline nanoparticles appears amorphous with this type of resolution is extremely narrow. So it's very unlikely that each nanoparticle that we have observed turns out to be in an out of Bragg condition orientation each time it goes below 2 nanometers. And additionally, I did not show this result, but we have also a lot of image of the phase transition where we see at the beginning the particles are monocrystalline, and we see in a single nanocrystal areas that are amorphous and areas that are crystalline. So it means that at some point we catch really the diffusion of the crystallization of amorphizations. So it clearly means that we have a phase transition here, and the fact that we observe both type of area amorphous and crystalline within the same nanoparticles prove that this phase transition is not due to the orientation of the nanocrystal.
Cool, very cool. I like that you were able to prove that as well, because I guess it's really hard to prove if they're actually in or out of focus, if they're in or out of crystal plane, or if you have enough resolution. So that's awesome.
The resolution resolution is good enough for sure, but
that's good.
Orientation may have been a problem, but to me it's clear that all you see on this image how all those nanoparticles that are amorphous, I mean we have tons of data of them, how could they all be out of Bragg of orientation? It's extremely unlikely. So yeah, to me we clearly have a phase transition.
Awesome. I'll do a final question, and then I'll send you the rest because there are more. But a final question is about the spatial resolution in liquid phase TEM, because it's often limited by liquid Brownian motion, making it difficult to resolve atomic spacing despite aberration correction. Do you know if there's any way to retrieve the atomic scale information in real time or during post-processing, taking the Brownian motion into account?
Okay, we are working on it. So far we have published the result showing that we can improve the signal to noise ratio, but now we are working on this super resolution imaging, where we would have extremely noisy high resolution image, either in STEM or in TM modes. And the idea is to use exactly the same strategy, work on the numerically produce images to train the neuronal network and be able to improve the resolution and recover a noise-free high-resolution image, starting from extremely noisy high-resolution image. So that's on its way. It works. So far, it works. We are happy with the result. We just have to I mean, carefully analyze all the data and the effect of the machine learning approach on the how your image stay quantitative before publishing the result. But yes, it's on its way. It might be possible.
Very cool. Very, very cool. Well, there are a couple more questions, but I'll email them to you so you have everything together, and then you can answer the people personally.
I'll be happy to answer it.
Perfect. Thank you so much, Damien. It was an awesome presentation. Thank you for everybody for coming. Yeah, and this presentation will also be coming up on YouTube soon, so then you can either rewatch it 1,000 times if you really liked it, and please sign up for the other webinars as well. Damien, thank you so much again.
Thank you very much for inviting me. It was a pleasure.
Of course, and everybody have a really great evening, day, night if you're in the Asia region, and see you in the next one.
Bye. Thank you.
Bye, guys. Bye.